Yeah, it is.
When we draw this product out as hyperbolic GGC.
There is version of Ptolemy for that. And then one something is called white.
Yeah, really? Yeah.
This is when you have this hyperbolic or cycle.
Yeah.
Between your cycle. This is the same. You see. Now, what would you do for other disciplines? Too fast.
Relations are still obviously
Short relations. So you just
the relation is still between 6 arms, which form quadrilateral. Some of the vertices.
Yeah. So
And only 4 labels are involved.
does she know she's at the center of the scale?
She might.
That's okay. She knows she's at the center of the scale. You see everything she does. I see.
Sorry?
Yeah, I don't understand it. Why is it that we see this?
Because
That doesn't.
somebody on this computer pinned to the speaker.
This particular
So
she was the last speaker.
Yeah. Or if you choose, right, then you make it out. So we had this and start snoring. It's a snow detector.
Yes, well, that's good.
Yes, and also you randomly my keyboard and
Well, you have no idea what we did.
Yeah.
So it's a particular button that you
One of the function keys.
And there's stuff like but I very
who is this one?
You mean
So was it easy to
okay, let's start. Very good. I mean, you can't fly. So I could take my cat to take my really like which I don't took two ferries. So there are two ferries associated to the UK. One goes to Newcastle.
You are not in school.
It's possible that
Okay, yeah. So you
yes,
say
so two ferries, one from Amsterdam to Newcastle, and one near Rotterdam. Second.
so. This is shorter than
Yeah.
France.
I mean, it's closer to me than
Starting in Amsterdam. Which is
no, it was fine. I have to choose. That's correct. Which is like 6.5. Yeah.
89.
Yes. So, I mean, it's really nice.
How was the
Because Newcastle
this 8.5?
Oh yeah.
you feel it? It's very big enough.
Okay, so can you hear me? Yeah, maybe it's time to continue with the next talk of the afternoon, and so it is Zhou from Tsinghua who will speak about connectedness of the support tau tilting graph of a gentle algebra. Thank you.
Okay, can you hear me? Hello? Yeah. Okay. Thank you, and thank you for the introduction, and thank the organizers to give me this opportunity to speak here. So let me share my slides. Can you see it? Yeah. Okay, thank you. So this talk is based on my joint work with Changjian Fu, Shengfei Geng, and Pin Liu, and this paper is already on the archive. So in this talk, we will talk about the connectedness of the support tau tilting graph of some algebra, especially for gentle algebra. So first, let me speak some motivation or backgrounds. So Bowen, Marsh, Rennick, Wrighton, and Todorov introduced the class categories, where they showed that the exchange graph of class tilting objects in a class category of hereditary algebras is connected. And recently, in Fu and Geng's work, they generalized this result to the class category of hereditary class categories with tilting objects. And in the geometric aspect, by forming Shapiro-Thurston's work and also by Bruce Lee Zhang and my joint work with Chu, we can show this result for class categories arising from triangulated surface with non-empty boundary. And also recently, Adachi, Yama, and Wrighton introduced the tau tilting theory, which can be regarded as class theory for arbitrary finite dimensional algebras. So we want to study a similar thing, but for the exchange graph of support tau tilting modules over some finite dimensional algebra. Okay, then let's fix some notations. First, K is an algebraically closed field, and A is a finite dimensional K algebra. The module A denotes the category of finitely generated ret A modules. And the cardinal number of M is the number of non-isomorphic indecomposable summands of a module, A module. And project A denotes the category of finitely generated projective ret A modules. And finally, tau is the Auslander written translation. Okay, then first, let's recall the definition of tau tilting theory. So a pair of an A module M and a projective A module P is called tau rigid if there is no non-zero map from M to tau M and no non-zero map from P to M. Such a tau rigid pair is called support tau tilting, or tau tilting for simply if the number of isomorphic, non-isomorphic direct summand of M plus Z of P is equal to Z of A. So a pair MP is called basic if both M and P are basic. And the pair is called indecomposable if it is basic and the candidate number is equal to 1. And also another pair NQ is called a direct summand of this pair MP if N is a direct summand of M and the Q is a direct summand of P. So indeed, it is known that for each tau tilting pair MP, the left part M is called the support tau tilting modules. And an important thing is that there is an operator on the basic tau tilting pair called mutation, which is another basic tau tilting pair that has the same indecomposable direct summands as MP, except one indecomposable direct summand. So we can define an exchange graph of tau tilting pairs whose vertices are basic tau tilting pairs up to isomorphism and whose edges are mutations. So by Adachi-Yama-Retten's result, we know that this exchange graph is irregular, where N is the rank of A. Okay, so if we go back to the class categories, we will know that when A is two-calabial tilting algebra, that means A is the isomorphism algebra of some class tilting object T in a class category C. Then the corresponding exchange graph is the same as the exchange graph of class tilting objects in C. So in this case, we go back to the classical cluster theory. But for an arbitrary finite dimensional algebra, our question is when this exchange graph is connected. So to study this, we need another notion which is related to the connectedness. That is tau-reachable property. So two indecomposable tau-reached pairs, MP and NQ, are called tau-reachable from each other if there is a sequence of tau-rigid pairs, M0, P0 to MS, PS, such that the first one is MP and the last one is NQ. And moreover, each neighbor, neighbors, two neighbors, MI, PI, and MI plus 1 and PI plus 1 should have non-zero common direct summand. And if for any two indecomposable tau-rigid pairs, they are tau-reachable from each other, then we call the algebra A has the tau-reachable property. So an easy observation is that if the exchange graph of tau-tilting pairs of A is connected, then A has the tau-reachable property. Yeah, this is because for any two indecomposable tau-rigid pair MP and NQ, you can first take a compilation of MP to a tau-tilting pair, and also take a compilation of NQ to a tau-tilting pair. Then you can do the mutation because the exchange graph is connected. Then you get the required sequence. However, the converse of this implication is not known.
你有那个窗帘吗？
For now, we only know that if A has the tau reachable property is a necessary condition for the connectedness. So we don't know how about the converse. Okay, now let's first see some examples about tau reachable property. Okay, first, if we consider two indecomposable tau rigid pair, MP and NQ, and if we consider their direct sum, if this one is tau rigid, then these two pairs are tau reachable from each other. This is easy because you just take this sequence and the first MP, then their direct sum, and then the other pair. Okay. Second, if M is not sincere, that is by definition, there is some non-zero projective A module such that there is no non-zero map from P to M. So by the first case, we will know that M0 is tau reachable from 0P because MP is tau rigid. This one is tau rigid. Okay, so from these two, we know that any indecomposable tau rigid pairs, which is of the form either of the form M0 with M non-sincere sincere or 0P with P projective, they are always tau reachable from each other. Okay, so the only pair we need to care about or study is pair M0 with M sincere, right? Okay, so we can get the following lemma. That is, if we want to show that A has the tau reachable property, it's sufficient to show that any sincere indecomposable tau rigid module M is tau reachable from an indecomposable tau rigid, another indecomposable tau rigid module N with smaller dimension. Yeah. Then, I mean, if you can find N, then you can find, if N is still sincere, then you can find N1, which is smaller dimension. Then finally, you will get some NS, which is not sincere and which is tau reachable from M. Then that show A has the tau reachable property. Okay. Now we know how to check an algebra to be to have the tau reachable property. Then the next step is to see when we can, I mean, get a converse implication that if we can show A is has the tau reachable property, can we see that the exchange graph is connected? To do this, we need one more notion using the tau reduction introduced by Hassel. So that is, for any tau reachable pair MP, we consider the Bangas compilation of MP. And we call the isomorphism algebra of the corresponding super-tau tilting module T, the tau reduction of A with respect to this given tau rigid pair MP. Then we introduce a new notion that is A has the totally tau reachable property if any tau reduction of A is tau reachable. Here I need to add some words. That is, we need to require that this tau reduction of rank bigger than 1, because if A is just, I mean, A is indecomposable as A module, then it is not tau reachable indeed. Okay, then we can show that as our first theorem, the algebra A has the totally tau reachable property if and only if the exchange graph is connected and has one more property, the so-called reachable in phase property. What's that? So the exchange graph is called has the reachable in phase property if when there are passes in the graph between two basic tau tilting pairs M1P1 and M2P2, then there, and for any common direct summand NQ of them, then there must be a path in the graph between M1, P1 and M2, P2, such that each vertex this path going through should have NQ as a direct segment. Indeed, we know that if you consider a full subcategory, the full graph of this exchange graph consisting of the basic tilting pairs, which has NQ as a direct segment, we will get a face of this graph. So that's why this property is called reachable in face property. And also I want to give a remark that if A is tilting finite, or it is two Calabi tilted, that means it is an isomorphism algebra of some class tilting object in class category, then this exchange graph has the reachable in face property. Okay, so now we know that if we can show an algebra has the totally reachable property, then we can prove that the exchange graph of its tilting pair is connected and also has some reachable in face property. But I mean, also just now I show you how to check an algebra has the reachable property. Then one problem is that how to to compute the reduction or to check it is has the totally reachable property. But this thing is good, is very good for a special class of finite dimensional algebras, the so-called gentle algebras. So the gentle algebra was already introduced in the Carrie's yesterday's talk, so I do not want to repeat the definition. But I want to say there is an important observation, that is any reduction of a gentle algebra is still gentle. Okay, so that means if we want to show that any gentle algebra has the totally reachable property, it's enough to show that any gentle algebra has the reachable property. Okay. Okay, then recall that how to prove that an algebra has the reachable property. It is enough to show that for any sincere module, a rigid indecomposable module, you can find another indecomposable rigid module with smaller dimension. To do this, we need to use a geometric model for the module category of gentle algebra. I also want to mention that in the Carrie's talk yesterday, she also mentioned a geometric model for gentle algebras, but that one is for the direct category of gentle algebras or property category of gentle algebras. But here, this model is for the module category of gentle algebras, which is from Fermi, Shapiro, Thurston's work and some other people's work. These two generic models can be related by some so-called Calabi X category, which is contained in my joint work with Chu and Akishi. Okay, now let's focus on our geometric model for the module category. So a marked surface, is a pair where S is an oriented connected surface with non-empty boundary, and M is a finite subset of the points on the boundary. And a curve of the marked surface is a curve of the surface whose endpoints are marked points in M, and which is homotopy to neither a point nor a boundary segment. And for any two curves, or maybe they may be the same. Okay, for any curves gamma 1 and gamma 2 on the surface, which are in a minimal position, we can define the intersection number between these two curves to be the intersection, the number of the intersections between these two curves in the interior of the surface. Then we call a curve an arc if it has no self-intersections in the interior of the surface. And we call two curves, gamma 1 and gamma 2, non-crossing if they do not have intersections in the interior of the surface. Okay, Then we can define what is a partial triangulation T, which is a collection of non-crossing arcs on the surface, on the marked surface, such that it divides the surface into polygons like this, or a monogons with an unmarked boundary commutant like this. Just see the red curves, arcs, and the diagonals with an unmarked boundary component like this. Then we defined a permissible curve with respect to this partial triangulation. It's a curve on the marked surface satisfying the following condition. That is for the, a very long line, okay. For its end segments, it should, each end segment should have one of the forms in these three pictures, depending on which regions it belongs to. And for the internal segments, it should cut out an angle from the partial triangulation. Okay, this is what is called a permissible curve. Then this geometric model was introduced indeed by Barr and Simmers. They show that for any general algebra A, there is a marked surface SM with a partial triangulation T, such that there is a bijection between the permissible curves and the so-called theorem modules. Moreover, the vector consisting of the intersection numbers between arcs in T and the curve gamma is exactly the dimension vector of the module corresponding to the curve gamma. I should remark that indeed the permissible curves defined in BS paper is a little different from the permissible, this definition which I mentioned here. Yeah, but there are some, they are equivalent in some sense. We use this, our definition, because this can easy to produce the following intersection dimension formula. That is, after their work, Pinghe, Binzhu, and I proved that for any two permissible curves, gamma 1 and gamma 2, we can show that the intersection number between gamma 1 and gamma 2 is equal to the dimension of the home space from the first module, which is the module corresponding to gamma 1, to the AR translation of the second module. Yeah, the second module is corresponding to gamma 2, plus the dimension of the home from the second module to the AR translation of the first module. So as an application, we have the following geometric model for the tau-tilting theory for general algebras. That is, we have bijections. The first one is between the set of permissible arcs. Yeah, that means the curves without self-intersections in the interior, and the incomposable tau-rigid modules. And this also gives a bijection between the collections of non-crossing permissible arcs and the basic tau-rigid modules. Okay, then we can use this to show that the general algebra has tau-rigid property. How to do that? So fix the marked surface and the partial triangulation in the previous theorem. The key lemma is that for any permissible arc gamma, satisfying that the intersection number between gamma and any arc in T is non-zero. So that means the corresponding module M gamma is sincere and indecomposable and tau-rigid, right? So for this gamma, we can find either a permissible arc gamma prime, another permissible arc, such that it is compatible with gamma. That means M gamma prime direct sum M gamma is tau-rigid by our results, and with smaller dimension, right? So this what we want. Oh, maybe we cannot do this by just one step. So in another case, we have permissible arcs gamma prime and gamma prime, such that in the first step, we have that gamma prime direct sum gamma M gamma is also tau-rigid, but with the same dimension. However, then we can do the second step to get another module, which is tau-rigid from gamma prime with smaller dimension. Okay. Okay, so by this key lemma, I do not want to mention how to prove it. You can see our paper, but you can see that this we just use this geometric model to show that any sincere module can be tau-rigid from another one with smaller dimension. Then by what we discussed just now, we can show that the gentle algebras has the tau-rigid property. Okay. Also, we already mentioned that any tau reduction of gentle algebras are still gentle. So we have the second main theorem, that is the gentle algebras have the totally tau-rigid property, and hence by the first theorem, their exchange graph of tau-tilting pairs are connected and have the reachable in phase property. Okay, I want to remark that this result is known for the gentle algebras, which arise from full triangulations of microsurfaces, proved by Bursley and John's paper. And indeed, in their paper, they show more. That is, they prove that for any two vertices in the graph, the shortest path between these paths must be in any phase containing these two vertices. Okay, finally, I want to give some remarks. The first one is, indeed, in my joint work with Pinghe and Binzhu, we give the geometric model, that means the bijection between objects and curves, and also the intersection dimension formula, not only for the module category of gentle algebras, but also for skew gentle algebras. So we are now also considering the exchange graph of tau-tilting pairs for skew gentle algebras, but somehow in a different approach, partially because the tau reduction of a skew gentle algebra is maybe not skew gentle. Okay, so this is what we did, and using some methods as a connectedness of the exchange graph of the flip of triangulations. Okay, another remark is about Dugas' work published in this year. It is shown that the exchange graph of tilting complexes of gentle algebras may not be connected. So note that the relationship of our exchange graph and the exchange graph of tilting is that indeed our tau-tilting exchange graph is a full subgraph of the exchange graph of tilting complex of A, consisting of the two-term tilting complexes, right? Because there is a bijection between two-term tilting complexes and the super tau-tilting modules, and also the tilting tau-tilting pairs. Yeah, so that means we show that this subgraph is connected. However, the whole exchange graph maybe not. Okay, thank you.
Okay, thank you very much. Are there any questions? So I don't know if somebody in the room want to ask a question, or there was a question first, yeah, maybe in the chat, sorry, by Hippolito, who asked about the definition of Russell's tau reduction. So is there a mistake in the definition?
Let
Or?
me see. Yes.
Maybe I can ask the question for the one who do not have any computer here. So shouldn't we caution the algebra AMP by an idempotent idea?
Quotients the algebra quotient by an idempotent idea. You mean okay? Yes. Yes. This is possible. I mean, by Russell's definition, I mean the original definition, he just take some tau-rigid objects, not a tau-rigid pair, and he considers the Bangard's compilation of that tau-rigid objects. So in that case, the quotient is not by some idempotent ideal, but in our case, we admit that. I mean this. How to say? I mean, for example, if you take 0p for some projective module p, and if you take the Bangard's compilation, you will get the direct sum of the projective without p. And then when you consider the isomorphism algebra, that is just to take, yes, the isomorphism algebra of the other part. But,
yeah, what I meant is that.
Yes, sorry.
Yeah, sorry. No, it's that in general, the Hasso construction has yet another step in which you quotient this endomorphism algebra by the idempotent, which is associated to the original tau-rigid module, right?
Yes.
You take the Bangard's completion of your tau-rigid object, you do the endomorphism algebra, and then you quotient, and this is in order to have the right rank to have the completions of your tau-rigids.
Yes, you are right. Sorry. Sorry, that's a typo. Yes. Thank you. Yes, we need to quotient by that. Yes.
Yeah. Okay. Yeah.
Okay. So, any other question, or maybe from people? So, is there a question in the room? So maybe you can, yeah, I don't know, send some people close to the computer or something, because we cannot hear very well.
Where's the microphone? I don't know if you can hear me. Can you hear me?
Yeah.
Yeah, it's not there. Yeah, we're getting it. You can hear. Do you mind giving some of your alternative strategy in the skew generator?
Sorry,
I think
didn't hear it's clear.
So the question is whether you can explain what would be the strategy for the skew gentle case, because you explained that you couldn't follow the same strategy because by reduction you lose the property to be skew gentle. Okay, so what is the strategy then?
Then I mean for skew gentle algebra, you mean we how to say, we just consider I mean, because each let me see, the total tilting pair corresponding to some maximal collection of non-crossing permissible arcs. And then we study how to mutate the maximal collection to corresponding to the mutation of support tilting. Then we just let people, I mean, you know that the exchange graph of flips of triangulation is connected. So we use some similar method to show that the exchange graph of the mutation of the maximal collection of non-crossing permissible arcs. It's this, I mean, that's what we do for skew-gentle algebra case. I mean, just to get the connectedness from the geometrical model directly.
Thank you.
Yeah, thank you.
So
Actually, have another question.
yeah, please.
Yeah, it was with respect to the geometric model that you're using. Do you have some kind of nice interpretation of the tau tilting reduction? I mean, suppose that you start with a curve corresponding with to a tau rigid object in the composable tau rigid object. Would it be that the tau tilting reduction would give you exactly, you know, cutting along this curve or something like this?
Yes. That should be. But I think I mean we have not I mean prove it or I didn't see somebody to prove it. Yeah, it should be.
Thank you.
Thank you.
So, any other question? No. It doesn't seem to be the case. So let's thank the speaker again. And so now there is a coffee break or something. And we should, yeah, we should meet maybe in 25 minutes, I think, according to my schedule. So see you later then.
Ready?
Maybe can I move this by tomorrow for now? I mean, we can.
So you don't need to do very much.
We have to be careful with that.
Yes, no, this
Yeah,
is also-
whatever I said.
It's probably how it works.
You're gonna see.
So, yeah. What you do is these days everyone has problems with detail.
I think you're gonna see us. We will have a 7. Well, we will have a 7 starting soon. There was no one else. No, you didn't. You couldn't. But you are on the list. You forgot to say.
Most important resource in the desert, zooming by a long way.
Oh.
Yeah, when is the something? Oh,
In some places.
so this one you have to choose. Want to speak? If you want to speak.
So this would be also.
Why not?
They certainly spent a lot of time engineering movement of water around. And the Muslims also. See,
Yeah, so glasses of water.
have you ever been to southern Spain?
Yes.
New Granada.
Oh, there is
They
this.
have some very impressive aqueducts that come from the mountains near Granada all the way around, I think probably all the way to Granada. But also through the kind of intermediate lands, so that you can do that. You know, these spaces. So often you have this peculiar situation that you walk up to the top of a ridge. And of course, there's some small stream at the bottom of the valley. You walk up to the top of the bridge, and then on the top of the bridge there's essentially a canal that's quite a wide aqueduct. The water is on the top side.
So I remember going to this place of
Where is your accommodation?
there's a focus. The Catholic
Ferdinand and Isabella.
Charles?
So we had some place where
Yeah.
Segovia.
Okay, so
Segovia, yeah. There's a big Roman aqueduct in Segovia.
That's home.
Yeah, I think that's Roman.
not
I think Segovia is yes. Yes, Segovia is very interesting.
really.
It's sort of almost hill-topped.
I think
Fortress is one end.
Yeah, I have a.
So, but there is a Saint. But
My daughter.
like, how was that? You were running to Saintburg.
Was
You
this
were
that's an
running one
excursion?
with Saintburg.
Yes.
Kind of a canonical
Saintburg,
excursion.
yeah, exactly. It was.
Excursion place, and then you go and have dinner.
But yeah, one way is to do this.
But maybe you didn't. Maybe you didn't do that.
But the. So, okay, so this was in, it was a conference in.
So I don't know exactly, but that's the
So
cabbage.
one of the excursions was to go to school.
Yes, yes.
So we went there, so my daughter was 2 years. And so we were there.
Yeah,
She decided to go to the throne.
Yeah.
And it was fast. But she was. And she was playing around. It was a phone.
but then I then.
See these things, especially since she's Jewish.
That was in the evening.
Right.
She's well known
On Friday.
It's Belgium of the
Yeah, when
Jews.
we have.
Yes, was it?
Yeah, this was the Spanish. This
From
Yeah,
Toledo.
he was there.
Everyone,
We were
everyone
having
was
all
was
this and we called him.
was so 1492 is a member of the
No,
One of these.
no, I just said, oops, now I'm gonna be late.
So this led to the notion of.
But yeah, I mean, this is a bit nice, but of course it's all very flat.
The problem is that obviously the microphones are.
Starting in Spain.
Yeah, that's, I mean, I usually go to here. So she
Not
doesn't
just,
she also
not
goes
just
to
one.
the
group.
and then a lot of
So there is
The
a
microphone doesn't have multiple words, suddenly from a five microphones.
and she goes longer and then the comes here.
Okay. So you can identify.
distinction.
Green is just green light, or is it warm? Is it heat?
coming from
Oh, okay.
this.
You're great. I mean, I run past it.
Obviously, if you put 3
Because-
people per table.
So, yeah, here it is, Jesus green light.
Together, and this is the one that's right in the middle, so that would work.
Oh,
But obviously,
Okay.
2 per table, you suddenly.
Even though the Jews were, even though the Jews were
Oh, yeah, I
exposed
walked
by the Christians, not by the Muslims.
someone, I was just,
They ended up
and
in
then
lots of
it has some meadows thingy, maybe it was in this
ended
direction.
up in lots of.
No,
And they
Oh,
went
here.
all the way, I mean, with time.
yeah, there was like children and everything. I mean, the one Jesus green light was very small.
In relation to
The other one bigger.
Is this the time when Benny ended up
No.
announcing it?
Yes.
How maybe we saw
Yeah,
that.
it's through there.
So you
I
can
think it
go
was
into the
must be calm. Maybe there are. But basically, yeah, basically Spanish throne expelled all the bank. And then consequently had no source of money left. They were to export.
They end up in Amsterdam and is giving service,
Yeah.
printing service.
So would you be okay?
Many of the Jews, because these are what is named.
3 per table, those 2 tables.
Yes,
Yes.
never expelled the banking sector, even if.
If those 2 tables.
Well,
have
in
6
the case of, this was King. One.
Yes, I mean, the British did this 100 years earlier. I forget what.
Yeah, even maybe
I'm
even.
on late shift, so I'll.
Well,
That's the tomorrow.
Do you know what is?
I was thinking
I
maybe.
don't remember, I thought we saw some documented,
We can put
don't, I think.
one camera.
Because in his case, it was a different reason.
Yeah.
They wanted
Maybe
to
that's
agree that it's that.
just the first.
Yes, well, yeah,
Decided to
that's
kill.
The ones who are online.
expel all the, and then not being back. Yeah,
That's
But
easy
it's
way out.
impossible.
Yes.
It's not a long term solution.
I had a French, one of the French princes as well.
Oh. this is-
Basically, I don't know if it was Jews, but whoever it was, that may have been the 10th of them. It was a French king.
So we will get 1 camera per whiteboard.
Or.
So would you be happy to lose
One reason was because he
the
had.
back feed of the whole room in order to get the second whiteboard?
I would prefer to have a second level, but whiteboard instead of.
Okay, yeah. Because we can just put a small table at the front with a laptop and a camera and a tripod. We can make it quite small. And yeah, then you'll
Well, one
have.
of the tiny ones.
Yeah. Same thing. Okay, yeah, we can do
We're
that.
gonna try, so we stay after, we try to, so you stay after this.
I mean, James is here till.
I'm here till 10
tonight.
PM.
He will be doing the
It won't take that long, don't worry.
Hello, Brad. Hey, so trying to solve the problem?
Yeah.
Can you stay a bit later? Rearrange deals and see if we can set 2 cameras, one for each blackboard or something.
Yeah.
And that's,
Always one.
yes.
How about 4 cameras?
Well, do you have 4 cameras?
4 cameras.
No. this-
We're running a lot of hybrid events at the moment, so we kind of maxed out in terms of, we could hire some more in, but obviously on such short notice, I don't know if we'll be able to get 2 more cameras for tomorrow morning.
Yeah, I don't understand why the nucleus. So is there not a lecture room which has nice boards?
Sorry, is there another lecture?
Is there not a lecture room which has boards installed at that wall?
Not here, not in this.
Not in this.
Because we keep every room as like a blank canvas, we can then put whatever setup the client needs. So we don't really have like whiteboards or blackboard.
So the mathematicians.
Yeah, because we use that more just for projection, really.
I'm thinking to say if we switch one to the front as we back.
Yeah.
And maybe we put one whiteboard there, the other one there.
Yeah.
1 camera each.
Yeah.
Then the only problem is that maybe they will have to switch.
With the camera and the online with the camera switch automatically. then there's any.
I don't think so.
No.
It's a problem. They have to switch.
No, so each person can choose their own viewing option, so they will have to pin each
So
camera.
you have to be with the ones that
Two
don't.
participants.
That's the only solution I can think of now. Like with what we have, try to make it more like what we expect.
Yeah.
Usually the Zoom focuses on based on the audio, speeds or something.
It does, but you can pin whichever camera you want to be like in the foreground.
And the microphone is associated to one of the two cameras.
It will be because one of the two cameras is plugged into the lectern, and obviously that's what's running the sound. So you can manually pin whichever webcam you want to be in the foreground, whether it's audio or not.
So if at home you have a computer and something else, then you could pin both.
Can that be like can that be the moderator say someone is?
We could sit next to each other. I have one screen with the other screen. We would see.
No, I mean, so someone is controlling the call, someone can like pin and unpin like you, for example, from here. If you're like the whatever.
I think
one for 5 minutes you just said this one, pin and then they switch to the other one. It's not like they're going to be one on the three, it's going to be like 5-10 minutes each.
Yeah, I know, but then you have to pin yourself.
yes.
But the question is, can that work be made from the one who's controlling the call, not each person?
Yeah.
I mean, you could just move it backwards, because obviously the third row is going to be roughly where that mixer is, so you should move it back if you want.
You can stay in the word you want.
Yeah.
Yeah, we start 5 minutes earlier with some training, like pin this one, now pin this one, now pin this one.
1, 2, 1, 2, 1.
Well, yes, that's if you figure out the right camera, then yes.
So are we happy with the classroom for tomorrow? Is that what we're doing? Yeah.
Yeah,
The
we'll
class-
try to set exactly what we've been discussing
Yeah.
later and test it. Go with that.
Okay.
Yes.
So for later, so we'll move that camera to the front, change it to classroom. Yeah. Okay.
Thank you.
No worries.
This is a good short. Because they think that this comes only when it's near the table. They can find. And also the moderator. That's what they.
No, they had some.
with two variables.
What we just negotiate, that is we want to set up the tables like this up to the last two. And two whiteboards each with their own camera. So just
Boxes, luxury boxes.
Hello?
Yes.
Can you hear us?
Yes, and you can now hear me, correct?
Yes, we can see.
Yes, we can see you very well.
Much is alive.
I love it, and I'm on YouTube. This is my big moment,
Yes.
my breakout moment.
Be careful because you're on YouTube, you'll stay on YouTube forever. Well, Chris, did you get my email? Yes.
I did, yeah, I'm gonna reply. I've just been sort of busy. I'm giving another talk today in the afternoon, which was an insane idea, but yeah.
Where?
At Michigan State, but it had to write all the slides for that too. So.
Oh, and I also got an email saying that apparently I'm involved in some topic at joint meeting, so I assume that was you.
I also got that email, yes. Which session is it?
I don't know, I wasn't.
Oh, so it's Trey who's doing it then. I see. Nice. Then I'll ask him.
All right. We'll let you. Cameras. Which one?
Мне сказал, что наоборот, что столы расставят так, чтобы быть редкие. Нет, в принципе, можно. А кто у нас сегодня четвертый? Точно. Не
Она же сидела с нами. То есть рядом со мной. Как торжественно. Второй порции не пришло. Завтра у нас. Завтра, Кристина. Завтра все среду.
Recording in progress.
Okay, so are you ready, Chris?
I am ready, yes.
So maybe it's time to resume and we continue the session with Chris Fraser from Michigan State University, and the title is Cluster Combinatorics of SLK Skein Algebras in the Presence of Punctures. So thank you.
Thanks, Claire, and thanks to the organizers of this week and the whole semester, and for the invitation to speak. Let me apologize by saying that my talk is not especially, or maybe at all, representation theoretical in the sense of this week. But it's an invitation to do some representation theory, and also it's a preparation for the talk which follows mine by Emine, which will use these kinds of ideas in a more representation theoretic setting. And it's joint work with Pasha Pilyavsky, who's at University of Minnesota. The paper is on arXiv, and this, if you can't find the slides in the chat, they're also on my website. Oh, what's the talk about? 3 things. So first, it's about a particular family of cluster algebras. These generalize the cluster algebras from surfaces, which I think all of us know, but that story is like the SL2 story, and I'm talking about the SLK story, so some higher rank generalization of that familiar story. I'm talking about the problem of cluster combinatorics, which means how do I label all the cluster variables? How do I decide when 2 are in a cluster together? And the kind of new stuff I want to talk about has to do with surfaces that have punctures in them, because there's some new combinatorial structures that arise in that case, and I want to identify those. We start with a familiar story, which is the construction of a cluster algebra from a surface, a marked surface, just like we saw in the previous talk. The surface has some mark points that they could be in the interior, in which case I call them punctures of your surface. You choose a triangulation of your surface. Inside each triangle, you draw an oriented 3 cycle, as I've done here, and that yields a quiver with frozen vertices. The frozen vertices are on the boundary. That yields a cluster algebra, and we know everything about these cluster algebras. So the problem of cluster combinatorics is solved. We know a labeling set for the cluster variables. They're in bijection with arcs in your surface. So they were called curves in the previous talk, but for me, an arc is something that starts at a mark point, winds around, and ends at a mark point. And a curve is something that does not end at mark points. Yeah, okay. And the statement I just made is only true when your surface has no punctures. We'll have to fix it in a second. The condition that 2 cluster variables are compatible is that they are non-crossing when drawn on the surface. And so the maximal sets of pairwise compatible cluster variables are the triangulations of your surface. We all know this. And also cluster monomials, we understand them too. Yeah. I take a partial triangulation and I'm allowed to repeat some curves. So you might call that like a multi-arc. Yes. Oh, and we also kind of, the preceding data is all indexing data, combinatorial, discrete data, but we also know how to work with these things algebraically. the algebra, the cluster algebra, it's the vector space spanned by products of arcs and curves, so monomials in arcs and curves. And you consider pictures such as those modulo these famous SL2 skein relations, such as the Ptolemy relation, which has been mentioned, for example, in Sierra's talk this morning, but many other times. And there are other relations, not just this one, but that's kind of the most interesting one. You can use these to calculate exchange relations or Laurent polynomial expansions, etc. When S has punctures, the story changes slightly, as we all know. Instead of this kind of purely topological data, you have to tag everything in sight to get the correct story. And I'll explain tagging on the next slide. All right, what's tagging? A reminder. It's a binary choice. So we have arcs, they end at mark points. If that mark point is a puncture, then you have to choose if you want a 1 at the puncture or you want a 2 at the puncture. Binary choice. At every endpoint of your arc, it's at a puncture. If you're at a boundary component, I don't care. Usually these are called plane and notched, but not for me today. Yes, okay, and how do I tell when objects like these correspond to cluster variables? How do I tell when they reside in a cluster together? I need to give you a binary rule. Here's the binary rule. If you ignore the tagging data, they need to be non-crossing in the usual sense, just like before. In addition, there is some kind of discrete rules. So if the arcs are different topological arcs, then they have to be tagged the same way anytime they end at the same puncture. If the arcs are this exact same arc, then they don't have to have the same taggings, but they can only disagree at exactly one end. So let me show you some pictures of these conditions. And I'd ask you to try to digest and memorize these conditions because I'll generalize them, by the end of the talk. So, right. Here is the kind of prototypical example of some compatible tagged arcs. They're the same arc. They have the same tagging at this puncture. They have opposite tagging at this puncture. These guys have opposite taggings at 2 different punctures. That's bad. These guys are different arcs with opposite taggings. That's bad. These guys are loops, which have different taggings, and that's bad. They differ kind of at 4 legs, not just at 1 leg. Yep. So all of these things are forbidden. Well, this one is the prototypical good example. And just as before, we can work with these things algebraically. So the main relation you need to know is the meaning of tagging an arc at a puncture is that if I take that same arc but don't tag, then when I multiply these 2 things together, I can express it as an element of the skein algebra that doesn't even touch this puncture. Okay, and so, algebraically, the meaning of this thing is that it's the Laurent monomial, and these 2 things we probably understand, just ordinary arcs in the cluster algebra. Although this thing is a cluster monomial, not a cluster variable, because it's the product of 2 compatible cluster variables. Yes, okay. What is the context for my talk today? Joachim Goncharov explained that the story just described fits into a larger setting where for every surface and for every Lie group, you get some cluster algebra. Actually, they only did the SLK case, but the other Lie types are also known by this point. So for me today, this is an SLK talk, not a general Lie type talk. So we have this family of cluster algebras, depending on a choice of surface, but also on a choice of SLK. And if k equals 2, I get the preceding story. How does one construct these cluster algebras? Just the same way as before, but more complicatedly. So I choose a triangulation of my surface. Rather than putting an oriented 3 cycle inside each triangle, I put this triangle of triangles, hive quiver it's sometimes called, inside every triangle, and I glue those together and I get some quiver drawn on my surface, and that defines a cluster algebra. And I can flip edges and triangles, and those correspond to a sequence of mutations. This cluster algebra has a meaning. Its clusters provide you with rational coordinate systems on a certain moduli space. The moduli space of G-local systems with the extra decoration of an affine flag at every marked point. So I have an affine flag at this marked point, an affine flag at this marked point, and so on. And what's an affine flag? You've probably seen flags of subspaces before. An affine flag is just a kind of exterior algebra version of this. So I have a vector, I have that vector wedge another vector, and so on. That kind of data, a flag's worth, sitting at every vertex. It's not very important to me that you understand anything about this thing, except maybe that there are affine flags at every vertex. These cluster algebras are interesting from a lot of perspectives. You can see a lot of things from representation theory, like Littlewood-Richardson numbers, or the Springer resolution, or the quantum group, or things of this nature by considering special cases of the surface and doing some constructions with it. And maybe another thing, they're related to spectral networks, which is a thing from mathematical physics. When k equals 2, we understand completely how things go, and kind of it's a big question mark how to generalize these things to other groups. But I will talk about that question mark today. Yeah, and to first order, what should you think? You should think that the higher notion of an arc in a triangulation has to do with drawing certain pictures in your surface. And these pictures are called SLK tensor diagrams. And their definition goes back to knot theory and maybe Roger Penrose in physics. But yeah, they've been around. But here are some illustrations of SL7 tensor diagrams. I think every single example in my talk today will be SL7. So what are the rules? Well, I draw some bipartite graph in my surface. It's allowed to plug into the marked points. And its edges are labeled by positive integers. And the requirement is that around every vertex, the integers sum up to 7, or k. So 1 plus 3 plus 1 plus 2 is the number 7. So this white vertex is happy. And I don't care about the, there's no such condition at marked points, but instead you should think that if an edge connects to a marked point and it's labeled by the number 3, then in the cluster algebra, so remember there's this affine flag sitting here. And this edge of label 3 means that I'm kind of using the third step of the affine flag in my algebraic constructions. Yeah, I don't require that these graphs be planar. For example, this is a perfectly fine to consider non-planar graph. It has a self-crossing. Okay, and one should think that this is kind of like a cluster variable in this higher cluster algebra, but I'll say more precise statements below. Okay, this is really an algebraic gadget. So you can construct just as before. Before we had the algebra generated by arcs and curves, modulo skein relations, and there's a similar story here. So we consider formal sums of these pictures you can draw, and we impose certain relations which capture kind of some identities in SLK representation theory, which I'm not explaining or talking about. But these relations are known. And that's how you just add stuff formally, and you multiply stuff by superimposing diagrams, just stacking diagrams. So as an example, this is a SL7 tensor diagram. And this is a different SL7 tensor diagram. And I've illustrated their product. I just superimposed them. That's how you multiply things in this algebra. And when k equals 2, we recover kind of the story everyone already knows, because there's not a lot of freedom for how to make an SL2 tensor diagram. Basically, you just recover the idea of I can do some arcs and I can do some simple closed curves in my surface. Right, and I said that these pictures are supposed to be cluster variables or cluster monomials or maybe canonical basis elements. And here's well, there exists at least a precise statement of this expectation in the special case that k equals 3 and S has no punctures. And I think Emine's talk will be in this k equals 3 setting, although I'm not sure. Maybe she's done something for us. Okay. Okay. Right. What do Sergey and Pasha say? They say that every cluster monomial corresponds in this skein algebra to a planar diagram. Right. Okay. This is interesting because this algebra, well, first of all, I didn't say this out loud. I expect that this algebra coincides with the cluster algebra, and there's some way you can identify the two. Okay. So that's the background. Elements of the algebra are linear combinations of diagrams. It's interesting if every cluster monomial is not a linear combination with lots of terms, but rather just a nice, picture you can draw. That's a nice statement. It makes cluster variables something you can have in your head. So that's what Sergey and Pasha conjecture. And they also give an explicit combinatorial rule that says, if you hand me a planar diagram, I can tell you, is it a cluster monomial or is it not? Now, this rule is conjectural and it's nearly celebrating its 10-year anniversary of being unproved. So, humanity doesn't know if this is true or false, but I think it's true. And their algorithm, which kind of detects which diagrams are cluster monomials and which are not, is called arborization. For higher values of k, we still expect, why not, that every cluster monomial is a planar diagram. I certainly expect that. But the thing which is kind of missing is it's not so trivial to push these arborization moves to higher k. As in the course of the project I worked on, I found lots of arborization moves, but I definitely would not confidently state that I have found all such moves. Did I lose my internet connection? It said it was unstable, or am I okay?
You're good.
I'm good. Okay, so one thing I want to say is that I am not going to solve this problem in this talk, and it's kind of the 0th order thing that you should understand is somebody else or an oracle from the future needs to solve this problem for my results to be completely useful. But I'm sidestepping this hard issue and also this hard issue, which is that this is unproved, and trying to talk about the things which we can see that are there. Yeah. Okay. So what can we see that is there? So the question basically is, suppose we understood how everything worked for surfaces without punctures. How should things change when your surface has punctures? And the key input to this story, well, in the SL2 case, it's how to tag something. And we already know how to tag something, and the recipe is due to Goncharov and Shen. So every puncture carries a affine flag. And if you're familiar with geolocal systems, when I have a puncture in my surface, in a geolocal system, I can parallel transport around the puncture, and that gives me some matrix called the monodromy of the local system. So I have affine flags at punctures, but I also have matrices at punctures. And Goncharov and Shen identified a symmetric group action on the set of affine flags. To specify such a symmetric group action, I just have to tell you what does the simple transposition do and check the braid relations and check it's an involution. And so what does SI do? Well, it takes the ith step of my affine flag sitting at my puncture, and it only replaces the last part of it by this rule. So I kind of take the I plus first vector and I move it into slot I, and I hit it with the monodromy matrix minus the identity. And this vector is not well-defined. It's only well-defined modulo the earlier steps of the flag, but nonetheless, this recipe is well-defined and it's a symmetric group action. they are affine flags. I'm doing the A-type variety, not the X-type variety. There is also an action on the X-type variety. It's actually it's a lot simpler action that is more obvious. You're just permuting eigenlines. But anyway, on the A side, this is the correct action. And Goncharov and Shen prove that this funny linear algebra map that you do is a cluster automorphism, which means if you know some cluster variable, you can twist it by this Y group action and you get a new cluster variable. And when K equals 2, the symmetric group is Z mod 2Z, and this action you can check is the same as just changing the ones into twos or changing plane into notched. Okay, 10 more minutes. I think that's doable. So my next slide is intended to combinatorialize this action, this Goncharov and Shen wild group action on affine flags. So 2 definitions. So first, there is a notion of pseudo-tagging a tensor diagram. And then there is a notion of tagging. This kind of distinction is doesn't show up so much when K equals 2. So we have a tensor diagram. It defines some element of my cluster algebra. What does it mean to pseudo-tag it? Well, I need to find the punctures. I need to find all of the legs, which are incident to the punctures. And in this case, there's only one leg incident to a puncture. And that leg is marked by the number 2. So I'm using, in this picture, I'm using the first 2 steps of the affine flag at that puncture in this tensor diagram. When I pseudo tag it, I replace the integer 2 by the 2 subset, any one I'd like. I chose the one 3, 6, but you could do 1, 2, 1, 3, 1, 4, 1, 5, 2, 7, I don't care. But it needs to be a 2 subset of the numbers 1 up to K when you're working inside SLK. So you enrich every leg of weight 2 to a 2 subset and so on. That is a pseudo tagging of a tensor diagram. This generalizes the SL2 story. I was, marking legs by either 1 or 2, which are the legs always have weight 1 in SL2, and I'm just choosing a 1 subset of the numbers 1, 2. Okay, that's pseudo tagging. It's a kind of fishy operation. And then a very legit operation is tagging. So a tagging of a tensor diagram is a pseudo tagging which satisfies an extra compatibility condition on the subsets, which is that whenever I have 2 legs which emanate from the same puncture, I require that their subsets satisfy a Boolean lattice comparison. So superset or subset comparison. So this might be some part of some big complicated tensor diagram drawn on my surface, and all of its legs are marked by subsets of the numbers 1 up to 7, and they form a partial flag of subsets with repeats. And that's the kind of thing that would be called a tag diagram, not merely a pseudo tag diagram. But something bad would be like if I had like 1, 2 and 1, 3. That's bad. That's not a partial flag of subsets, because 1, 2 is not contained in 1, 3, nor the opposite. Yes, okay. You already know examples of pseudo-tagged but not tag diagrams, even in the SL2 case. It's just usually in the first sentence of your paper, you exclude these. So for example, we all know that you're not supposed to draw pictures like this in the SL2 story. So you're not supposed to draw loops whose 2 ends are notched differently. That's a pseudo-tag diagram, but not a tag diagram. But it still makes sense algebraically, actually. This diagram is perfectly fine, and in fact, it's a cluster monomial, but it's pseudo-tag, not tag, right? Because 1 is not contained in 2, and 2 is not contained in 1. What is the algebraic meaning of tagging or pseudo-tagging legs in the way I've told you to do? Well, you're supposed to do this Goncharov-Shen thing to the vector. So at this affine, at this affine flag, I see the subset 3, 6. And that means I'm supposed to bring the third vector of my affine flag down and bring the sixth vector of my affine flag down using U minus the identity matrix the right number of times. And then I do my algebraic stuff, but I am using this partial flag rather than the one I had before, or this flag, affine flag, rather than the one I had before. Okay. That's the algebraic meaning. And I will end my talk by saying 2 conjectures and 2 theorems that really have to do about the properties of this algebraic construction of replacing flags by kind of complicated stuff like this. So maybe let me pause for 30 seconds because I think I have enough time to say what I want to say today. So yeah, if there are any questions. And if not, that's great. So to pseudo-tag a diagram is to pick an M subset for every leg of weight M, and it's tagged if, moreover, they satisfy containment conditions. All right, here are our conjectures, and then theorems which follow them. Right, so the first conjecture I think of as being an extension of this Fomin-Piliowski kind of intuition, but to arbitrary surfaces and with punctures and arbitrary values of k, not just k equals 3. So the conjecture is that every cluster monomial in this family of cluster algebras is given by a diagram which is simultaneously a planar diagram and also a tag diagram. So at every puncture, all of the legs satisfy some compatibility condition. Easy thing to write down, hard thing to prove. This is a non-trivial assertion because what is a cluster monomial? It's a product of things. How do I multiply things? Well, I stack them. Oh, Sal, do you have a question or that's an accidental hand raise? Okay, no problem. If you do have a question, feel free to interrupt me. I multiply things by stacking them. When I stack things, they're typically non-planar and they're typically not tagged, right? I like stack a leg labeled by 1, 2 with another leg of weight 1, 3, and now they don't satisfy the containment condition. So a typical product of cluster variables is neither planar nor tagged, but I claim that modulo algebraic identities, you can transform it into something which is planar and which is tagged. And I've already shown you an example of this. Oh, I'm sorry, Sal. You can chat it. I can see the chat, but yeah. Later, that's fine. Okay, so this is a cluster monomial in the familiar setting, k equals 2 setting, and algebraically, it is equal to this thing, and this thing is planar, and this thing is tagged. So we already know this example when k equals 2, and my below theorem will generalize this kind of calculation, multiplying things together and kind of getting rid of their bad behavior, but for arbitrary SLK. Okay, so our first theorem says the following. So supposedly the good diagrams are the tagged diagrams, not the pseudo-tagged ones. For example, I conjecture that any good basis will consist of tagged diagrams, maybe not planar. The cluster monomials, yes, will be planar. The non-cluster monomials will probably be non-planar diagrams, but they should be tagged. If those are the good elements, we want to know how to write the pseudo-tagged elements in terms of the good ones. So for example, I multiply 2 things. How do I express it in the basis of tagged things? And I mean, our first theorem says that you can do this. So any pseudo-tag diagram is a explicit linear combination of tagged ones. So it is reasonable to believe that the tag diagrams are a basis, let's say. A certain subset of the tag diagrams are a basis. Because when I multiply things, I'm pseudo-tagged, but I'm claiming you can write it in terms of tagged things. Okay, that's called the flattening theorem because it's like a Grosvenor style proof where you have something complicated and you make it simpler, flattening, flattening, flattening until finally it's tagged. Okay, here's an illustration of what goes into that theorem. I'm nearly done. Okay, I'll be quick. Here is a product of, well, it's two legs which aren't compatible. They don't satisfy a condition. They're not tagged with each other. And you can express any such picture as a linear combination of 5 pictures. And all that's changing in these pictures is kind of how much you're winding around the puncture. And that has to do with powers of the monodromy matrix. It has to do with the binomial theorem. The numerator of this Q linear combination is the 4th row of Pascal's triangle. And the denominator counts standard Young tableau of rectangular shape. The length and width of the rectangle is determined by the subsets, how much they intersect with each other. That's the flattening theorem. And you iterate this algebraic identity to flatten things into tagged things. Because what I've done here is I've taken the subsets 1, 4, 5, and 1, 2, 3, and replace them with the subsets 1, 2, 3, 4, 5, and 1. And those satisfy a containment. 1 is contained in 1, 2, 3, 4, 5. Okay, so this is an algebraic rule for calculating in this cluster algebra. And some exchange relations look like this. I have to hurry, so okay. I think this will take 2 minutes. Second conjecture is, in my opinion, the natural generalization of this compatibility criterion which Fomin, Shapiro, and Thurston identified. So I suppose I have tagged diagrams. So there's a tensor diagram and there's some extra combinatorial data of its tagging subsets at each leg. How do I know when they're compatible? Well, the underlying things need to be compatible, just like before. And this is the thing that we don't really know how to do in general. We kind of know how to do in k equals 3. We don't really know how to do this in general. But let's assume somebody told us how to do it. Second, if the underlying tensor diagrams are distinct, then basically all their legs need to satisfy a containment when I stack them. So just stacking them needs to result in something which is tagged, not merely pseudo-tagged. And lastly, if they are the exact same tensor diagram, then their taggings can disagree in exactly one leg, and it has to be by a transposition. And this exactly generalizes the SL2 case. So here's a picture. This might be a cluster variable. It's plugged into the rest of my surface in some way. It has subsets 2, 3, 2, 2, 3, and 2, 3, 5, 6 at the puncture. But I could replace 2, 3 by 2, 6 or by 3, 6. And all of those guys would be pairwise compatible with each other, provided they were the exact same tensor diagram, just tagged the same way. And our last theorem is, well, if these guys are compatible, then when I multiply them, I should be able to change it and make it both tagged and planar. And our last theorem says this is true, and I'll just end by showing those pictures. So you can multiply 3 things like this and express it as a tagged and planar diagram. So, which is not obvious because when I superimpose these 3 things, you know, they're pseudo-tagged, not tagged. Okay, so here are the pictures, and that's the end of my talk. Just quickly, I'll say the pictures. These guys are pseudo-tagged when stacked next to each other, but I can express it as a 1, 2, 3 leg and a 1 leg plus some other spiraling junk, which is planar. And if I multiply, say, four legs together, which differ by transpositions, they have to look like this up to symmetry. And this is the kind of tagged and planar diagram, which computes the same thing. So it has a leg of weight 1, 2, 3, 4, 5, and 3 legs of weight 1. You can figure this out using just easy considerations. And then this is the way to planarize everything. Thank you. That's all. I didn't make a thanks slide. I forgot.
Thank you very much. So, any questions?
Chris.
Hi, Sasha.
Hi, I have a question.
Yes.
Oh, I think Bernard was asking.
Sorry, no.
Yeah, you can go.
Okay. Yeah, maybe Sasha, you can start, or I'm sorry, I didn't get to who wants to ask the question. So, as Sasha, maybe you want to ask a question? No.
Yeah, Nathan, good question. I'll respond to it. But I don't know if Sasha is, Sal already said I answered his question, but Sasha seems frozen to me. So let me take the opportunity to answer Nathan's question. I didn't address this just because of time. Yeah, our conjectures are proved to be true in all the finite mutation type cases. And there are interesting ones. So for example, I haven't been thinking about this for a while. If you take, say, a bigon or a trigon with one puncture and G equals SL3, or you take a bigon and G equals SL4, then these are elliptic type, I think. Well, this one's finite type. These are elliptic type, and the conjectures are true on the nose.
Chris, sorry, could you repeat that? My internet fell off.
No problem. So Nathan asked, are there any examples where we know this conjecture? Yeah, so there are. If you take some small n-gons with one puncture, this one has type D4, cluster type D4. This one has the cluster type of a sphere minus 4 points, as does this one. So this and this have the same cluster type, and our conjectures are proved to be correct in those examples.
Can you explain again about affine flags at punctures? Sorry.
Yeah, any specific question, or do you mean like what's the wide group action, or just what does it mean to have an affine flag at punctures? Or
no, I understand what does it mean to have an affine flag at puncture, but I was under impression that Falk and Goncharov and Goncharov-Shane only had the usual flags at punctures, just because dimension-wise, so the number of cluster variables they provide just doesn't accommodate for an affine flag.
Right. So yeah, let me explain that. It's an interesting thing. So on the X cluster variety, the one that's not Fomin-Zelvinsky style, you have ordinary flags at punctures. On the A-type cluster variety, you have affine flags, which adds k-1 dimensions worth of scalar, because you're allowed to, you don't just have vectors, you have like, you don't just have the subspaces, you have the actual vectors lying in them. Okay, so as you say, that increases the dimension, but the monodromy fixes the affine flag. And so we do not have generic monodromy around our punctures. We have unipotent monodromy around our punctures. And requiring monodromy to be unipotent exactly decreases dimension by k-1, which accounts for this.
Got it. Thank you. Yeah. Okay. Got it.
Yes. Okay. Thank you. Other questions? Somebody in the room or in the chat or what? No? So,
I'll ask one more question, Chris. That's all right. Okay. Sorry. So is it possible to put coefficients into this picture besides just the frozen, boundary coefficients?
Yeah. Yeah. I think no one thought about that. I think it's, kind of Ian is probably Ian Lee is the person who, if anyone understands this, he would be the person who does. But yeah, I think it's not just really not understood what to do. Yeah.
Thanks.
Yeah.
So no more questions. So maybe we can thank Chris again, and we should meet in 7 minutes for the last talk of the day.
Very nice talk, Chris.
Thank you. Thank you.
Hopefully we will talk after my talk. Oh, you're muted.
I haven't downloaded Sakoko successfully, but I'm going to try to go to this one if I'm able to figure that out.
I think there is a link they emailed.
I think my guess is that I used my wrong university account email, and so it blocked me. But I'll try to
I see.
get to the bottom of that.
It's a good bench for doing certain things. And we'd throw a lot of it in.
It's everywhere. It has a long life.
There's a permanent switch. Should destroy.
So these hybrid seminars are kind of strange now, because when it was all online, that made sense in one way, but now with the hybrid seminars, like, there's this room of people. I guess they can hear me right now, high room of people, but like you can't see them really unless you can't. It just sort of feels like there's this, you're outside of something.
Just people asking questions on the screen.
Not in the room.
And they hear our voices. Maybe I better stop.
Continue.
I was just commenting how strange it was to not be in the room, but still be able to be heard, but not really see any of you very well. I don't know whether you heard me.
Let's try.
People attending as well? Just you were just talking to people who are
One and they provide lunch and breakfast. So during the rest of the time, you could just
yes, absolutely.
So it was very, very nice. They provide.
This was for quite a long time.
4 years.
So it's a bit more like.
And you could choose whether to work. Bit like that.
Bit like this after this. After
Yeah.
this.
Yeah, the atmosphere there is different. It's America. It's a larger distance.
Where do you stay? You stay in Jefferson?
Well, the top, yeah, I came there to go to this conference. I came a couple of days earlier to see my friends. On Friday, before the Sunday, I was supposed to move to the 7th, and they sent me saying that you were the last remaining person participant in the conference. So the conference was over on Zoom. Kind of strongly hinting.
Well, it's not the same.
So it's different. That was different meeting.
Yeah. And
Because-
so I just stayed with friends.
You just stayed in New Jersey?
Yeah. Well, what I did was the flood, so it was always.
It was worth it.
Yeah, sure. Because where else would they see historical flood?
Yes, there was a hurricane that came from the Mexican Gulf. Went all the way to New York, and only in New York.
In New York. Yeah. So the streets. Well, subway was flooded, but I was in Jersey and just support small.
Hi, Claire. Should I try sharing?
The stream was white stuff.
Oh, you're muted.
Hi. Yes, you can try.
Let's see if everything works fine.
That was
Maybe this year?
Yeah, just before.
But when
This was a day you left.
There was a big flood in China somewhere where they were also flood at the end of.
This is in this season, every week you have some storm, mostly.
Okay, it seems.
Yeah, it seems to work. Yeah.
Then it hits the land somewhere and goes over the way. And depending on where it hits the land, it ends up on the other side.
So I will keep it as it is.
It's a standard book.
But so I thought you were present in Cambridge, no? Or
yeah, I am having visa issues. I actually plan to be there at the beginning of September, but the things that I cannot control, I don't know what is happening with my visa application. They don't. They're not responsive, and I don't have a timeline. I had timeline. They said we will get back to you by September 9th at the latest, but then they didn't. And then from then on, I'm just waiting.
Emine,
The quality is good.
Ja, wir sollen es dann auch nochmal machen. Ich hab's nicht
Not many people.
Yeah, because of this kind of communication.
Yeah.
There were some other actions that
okay, so if everybody's ready, I cannot really see the room, but it seems that the people coming back. So the last talk of the day is by Emine Yildirim, and it will be on cluster structures. So please.
Thank you very much, Claire, for introduction. And I'd like to thank the organizers for such a great conference and the program at Isaac Newton Institute. Also, thank you everyone for coming to my talk. I'd like to make a small announcement before my talk. So there will be seminar series at Isaac Newton Institute starting September 28. So they will held Tuesdays from 4 to 5 UK time. And the format will be like this conference. We will have speakers at Isaac Newton, and then people who want to join, they can join in the Zoom. So it will be a hybrid seminar series. And our first speaker is Emily Gnawan on September 28. So, and then we will send the announcement very soon with the links and all the information. Okay. Yes, I also put my slides in the chat, and I like to put 2 references in the chat. So the first one is by Fomin and Pliowski about tensor diagrams Chris just talked about. So you may want to see concrete definitions of these objects, because in the short talk, we didn't have really time to go over them. I will not as well. So, and then the other paper I'm going to send in the chat is by Jensen King Su about the categorification of Grassmannian cluster algebras. So these are the 2 main references for my talk. And this will give you a clue that what I'm going to talk about. So let's start. So so this is a joint work, ongoing work with Ian Lei from Australian National University. Yes, it's still an ongoing work. It's in early stage. So this project started last fall during the program New Trends in Representation Theory at HIM Bonn. So what we are trying to do is, so the Chris talked about these nice objects, and there are beautiful cluster structures coming from this combinatorial setting. So Chris talked about the different surface, but for me, I will always consider these nice tensor diagrams. Chris called them tensor diagrams. I will call them webs. but webs are just planar tensor diagrams. So these are the objects I'm talking will be the same as the CRIS. Yeah, so what I was, okay. So the first thing we have is Fomin-Pliowski's cluster structures in the ring of SLV invariants. This is what I wanted to say. I'm always considering the disk, but the things, as you will hear, they will be also a similar version of the CRIS talk. Yeah, so there is this nice combinatorics happening in the combinatoric of tensor diagrams and webs, which are related to the ring of SLV invariants. And on the other side, we have a very nice categorification of Grassmannian cluster algebra in the sense of Jensen-King Hsu. Then it's natural to ask, is there any relation between these two different settings? Because the cluster structure on the homogeneous coordinate ring of Grassmannian is just a special case of the cluster structures in the ring of SLV invariants of n tuple of vectors in a k-dimensional vector space. So yeah, so then it is natural to ask the Fomin-Pliowski cluster structure coincide with the cluster structures coming from the setting of Jensen-King. So actually, even in their paper, tensor diagrams and cluster algebras, Fomin and Pliowski states that thus the web basis, which is the main object that carries the cluster structure, thus web basis coincides with the dual semi-canonical basis of Lutzig. So then it is very natural to think about the Jensen-King Hsu categorification and try to relate if there is any connection. So that's the motivation. Of course, the classical invariant theory studies more general rings. So in the paper by Fomin and Pliowski, they look at this ring. It's not just Grassmannians. So their setting is more general. And in the paper, they work on three-dimensional vector space. And then in that case, they show the cluster structure in this ring. And yeah, in the paper, they conjecture that every such ring carries a cluster algebra structure. So they proved it in the case of three-dimensional vector space, because thanks to the beautiful bases they have, web bases, but they conjecture that every such a ring should carry such a cluster algebra structure. So it's quite nice, and having such a general conjecture motivates the question in the Grassmannians. Yeah, so this is what I just said. Yeah, the web basis is introduced by Kupperberg, and it's a basis for the ring of invariants for the three-dimensional vector space. And so the webs are the elements, and these are exactly as CRIS talk, they are nothing but planar tensor diagrams. Yeah, so a web is a planar bipartite graph plus some properties. The explicit definition is in the paper of Fomin-Pliowski. Yeah, there's no point of going in details, but I also like to show you some pictures. So basically, they are used to pictorially represent certain elements in the invariant theory. So here I'm showing you some webs, tensor diagrams, and so they are embedded in the disk. So in the Fomin and Pliowski, they also looked at, of course, general surfaces, but the paper I referenced, they only have the combinatorics. That paper includes combinatorics embedded in the disk. But as you've seen in Chris talk, these beautiful objects, these bipartite graphs extends to different surfaces. Here, one thing, like I have two different set of webs. Here I only have black vertices on the boundary. This means I'm only working with some power of the vector space, but a priority, since Fomin and Plialski work with this ring, the V dual VA. So a priority, we may have the points representing the vectors from the dual bases, dual space. So yeah, in their setting, they have this type of collection of webs. But I will be also interested in the webs in this looking, namely the boundary vertices are all black because these will relate to the Grassmannian cluster algebras. But I just want to mention that this combinatorics extends so these are elements in the ring of invariant, SLV invariant. So let's talk about one explicit example. So Grassmannian tree 6. The cluster algebra, in this case, it's type D4, so it's a finite type. And the invariants in this case are functions of 3 by 6 matrix, right? We have Grassmannian tree 6, so we have the minor of this matrix. They are the invariant, basically the determinant. And how a tensor diagram or a web represents an invariant, an element. So there's a very nice recipe in the paper I sent, but for instance, I just want to give one explicit example. Here we see a web, which is a tensor diagram, and it has 6 vertices because we are working in Grassmannian tree 6. And we have 3 edges. We only have this tripod because this is the simplest case that I can show you. And what this means is we are choosing 3 vectors here. So if I draw this diagram like this, connecting 1, 3, 4, that means I want to compute the invariant, this invariant, which has this vector, and this vector. So that the determinant of this will give you the invariant. And I can actually compute this invariant by just looking at this picture and doing some combinatorics. So there is a recipe by coloring these edges and choosing particular elements at each step and then adding up, and then it will explicitly give me this determinant. So these tensor diagrams, these webs, with a combinatorial recipe, they produce elements in the invariant ring. And it's really just choosing a certain coloring on these, and with respect to those coloring, choosing these, the product of these variables. And yeah, so in this example, we should have 22 cluster variables if you have already looked at this cluster algebra. And then in this case, 20 of them will come from this web, because we will have a choice. We can choose 3 vertices from the 6, and each of them will give me a cluster variable. And then there are 2 non-fluker cluster variables in this case, which are explicitly these 2 pictures. Okay. Yeah, so this is just a quick note. An invariant associated to a non-elliptic web is called a web invariant. So this is not really complicated. it is a little bit technical, but we just don't want multiple edges and a certain configuration in the web, because as Chris mentioned, there are skein relations. You can reduce webs and get somehow the reduced version of them, the most beautiful version of them. And then when you write the invariant, we call it web invariant. And as Chris mentioned, so Fomin-Clayowski conjectures all cluster monomials are web invariants. So it is really nice. Like I don't know if it happens to Chris, but as we discuss in this project, these are all conjecture, but we treat them as, okay, these are true, and we try to find things. It's sometimes we even forget that these are all conjectures, because I also do believe in that using these webs, we get these web invariants, and they correspond to cluster monomials. And I believe the Fomin-Clayowski conjecturally describe which one of them should be cluster variable even. So these are all conjectural procedure, but they work pretty perfectly. So we sometimes forget that they are conjecture. We assume them and somehow work with them. Yeah, so this is the story in the Fomin-Clayowski side. And then, yeah, so there's this nice, beautiful story, and it has nice cluster structures. Of course, on the other side, we show cluster structures in the context of representation theory. And what we are trying to do, we are trying to see if these two different cluster structure talk to each other. And in this case, we like to look at this categorification, in the Grossmanians. And I want to talk about the algebra that they are using in this paper. It's easy to describe. So what we have, so I have 6 vertices drawn in this skewer, but you can imagine I have n vertices in a circular fashion, and I put arrows between them in this fashion. So I have one way going this way, and then this way. So usually the arrows outside are labeled with x, x1, x2, x3. So I just write x, y, but this is x1, x2, x3. You can think of them like this. And then the arrow inside, it's y1, y2, y3, and so on. So we want to consider the path algebra over the skewer. And then we want to have some relations. So the relations are at each vertex we have, we should have xy is equal to yx. So as I said, I suppress the i's, but this is for each vertex. So we will have n relations coming from here, and n other relation coming from this. This k is fixed, and it is with respect to which Grossmanian you want to work with. And when you fix k, you will have n other relations. And this is basically saying, if, for instance, k is equal to 3, if I go 3 steps this way, it should be equal to going 3 steps this way with y's. Okay, and then, yeah, we take this algebra, and they look at the completion of this algebra, and they use the module category of this algebra to categorify the cluster combinatorics in the Grassmannian. So this is the reference I put in the chat. Of course, this is an infinite dimensional. The modules are infinite dimensional. It's quite technical to work with this algebra, but they have a beautiful description of modules in terms of ranks, and somehow the building blocks of blocks in this algebra are the rank 1 modules, and they understand them very well because they correspond to Fluker coordinates in the homogeneous coordinate ring of Grassmannian. So the rank 1 modules, which are in correspondence with the Blucher coordinates, are well understood. And all the other module have, every other module has a filtration using rank 1 modules. Yeah, so that we have this big collection of modules, but they can be understood using this strategy. So we have rank 1 modules, rank 2 modules, rank 3 modules. So these modules have filtration, and there is a very nice way to look at these modules. So I think I have time, I can show you a little picture. So yeah, for instance, in the Blucher coordinates, so to determine combinatorially the Blucher coordinates, for instance, what we do, we want to choose a K subset in N. And you want a similar combinatorial data in this other side as well. And then when you look at the modules, you want this like a simple combinatorial data to determine the module you want to work with. For Blucher coordinates, so you want a similar combinatorial data to identify the rank 1 modules. And so here I drew rank 1 modules. And so you can imagine our QWER here. I opened it up. So this is a circular QWER, but let's think that I opened it up. And then I'm writing the module over this diagrammatically like this. So so these vertexes, you can think of it, it's opened. And so so how do we determine these rank 1 modules combinatorially? For instance, if I again go back to the same example, Grassmannian tree 6, so I want to see the module corresponding to 1, 3, 5. So what we do, we draw the lattice paths in this lattice diagram, and 1, 3, 5 tells you the down steps. So here I have 1, here I have 3, here I have 5. So 1, 3, 5. So this is 2, this is 3, 4, 5, and 6. So these 3 down steps determine somehow my rank 1 module combinatorially. And then for all the other ranks, so Chris said in the tensor diagrams, what you do, you took these 2 tensor diagrams and then you stack them on the top of each other to find somehow the higher rank tensor diagrams. And here, the similar story, you have these rank 1 modules, and then you stack them in a certain way, and then you get higher rank modules. Okay, so this is very hand-wavy description of these modules, but since the Grassmannian cluster algebras, they're really combinatorial, even this module structure, they're quite complicated, but we can somehow describe them combinatorially in a very nice way. Okay, so, and there has been some studies on, rank 1 modules are really well understood, no question there, but there are recent papers on the rank 2 modules by many authors. Like I wrote one paper, I forgot to write the name of the paper, but by these authors, Bauer, Bogdanik, Elsener, and Lee. And then they do study the rank 2 modules in their paper. And they have a theorem. So they say that, so this looks complicated. We don't really have to understand what is this formula, but there is a number. And then they say that there is at most this number of rigid rank 2 indecomposable in the nice module category. of this algebra that I described. I think Eleanor also talked about this. So this is the same, the Cohen-Macaulay modules over this path algebra, but I think Eleanor used the capital F. But so this is quite nice because there's this number, we can compute it in the examples and see if it's true, and it's true, and it gives this counting on the rigid rank 2 indecomposable modules. It's quite nice, and then they actually conjecture that this should be exactly the number of rigid indecomposable rank 2 modules, and we do believe in that. This is, I think, true. And with Ian Lee, in the ongoing work, we found a one-to-one correspondence between rank 2 rigid indecomposable and certain functions in the Grassmannian, which can be pictured by webs. I mean, in the paper, like Ian used this notation for the functions, but basically these are just webs. They're another way of labeling or naming the webs. So I want to show an example. So for the rank 2 webs will look like basically these three webs. Like this is in this case, of course, I have Grassmannian 510, but what I mean is for the rank 2 modules, what do I have? I have this tripod in the middle, and then they will have these branches attached to the white vertices. So I ignore the disk, but you can think that they're all embedded in the disk. So in the rank 2 case, it's quite simple. You have a tripod in the middle, and then the leaves attached to these white vertices. So for instance, these webs I draw here, they correspond to cluster variables. And then I somehow illustrated the corresponding rank 2 webs. So as I said, we can label the rank 2 webs, the rank 1 webs with the lattice pad, only looking at the down steps, and the rank 2 ones are just stacking them to each other, right? So I have these type of pictures for the rank 2 webs. And yeah, so they're quite combinatorial as well. And then we were able to find a recipe to go from a web to the rank 2 modules. So this is combinatorial. One thing we want to do, of course, we believe that we understand the rank 2 webs and which are the cluster variables. And then you stack them on the top of each other, you get cluster monomials. You can resolve them using skein relation and so on. So that we know the web invariants correspond to these webs. And then in the Jensen-King-Su setting, there is also a cluster character formula. So we can put these modules into a formula and find out what are the cluster variable corresponding to these modules. It's still a difficult question to check if they coincide, namely the cluster variables I get from these web invariants are the same as the cluster variable coming from the corresponding module. But we hope to also investigate this further. And actually, like the whole point was to see, okay, we have this cluster variable and we want to say this is the corresponding web and this is the corresponding module to the same cluster. And so this correspondence is actually more deep. So this is all what I want to say. Thank you very much.
And thank you very much. Are there some questions? Maybe first in the room. Yes.
I just wanted to clarify the last thing you were saying. You know, presumably the tripods for higher K, the things corresponding to look coordinates, you presumably do know that the function is the cluster character of the model. Is that right?
I couldn't really hear it very well, but if Claire, you
No, I also had trouble to can you repeat, please?
Know that the CC map works out for Pluker coordinates.
Yes.
Yeah, I think I haven't computed it, but I'm sure. I think we have did some actually way back when I was a PhD student. We did some calculation, and I remember that I think that the for Plukers, it is I'm sorry, I'm vague, but because we were trying to write a computer program to check higher, like rank 3 modules corresponding to rank 3 webs, somehow these more complicated webs. And then even that was the case. We computed one rank 3. So because of that, I believe, I don't remember the computations, but I believe they should coincide.
Well, the point was that if you know that, and you know that the bijection you have commutes with the mutation, then you know it's for all reachable objects by the multiplication. Because there is a constant.
So did I again have hard time to hear, but did I understand? So you start with the Plukers and then you mutate and you get all the others?
Well, that's what I'm sorry, I don't know where to point my voice so that you can hear it. As long as your bijection between webs and modules respects mutations, then if you check that the functions agree on Pluker coordinates, then they agree on all reachable things.
Mm-hmm. Yeah. This is one thing. I think we should work on to like if it respect the mutation and because I mean, okay, we are trying to see these mutation dynamic using rank 1 modules, and so using rank 1 modules we get these certain rank 2 ones, but there were some difficulties on the way because I don't think on the module side I still understand how the mutation goes with the rank 1 modules, like how if I iterate it. I think in the web combinatorics side, Ian knows how to mutate this rank 2 functions in the Grassmannian and what you get. He knows all of them, but I should work on the representation side more, like start with a seed of rank 1 modules mutated and get all rank 2, rank 3. I'm still trying to understand how this works.
Right.
Okay, any other question?
I can ask a question.
Sure.
Can you show your slides again?
Yeah. Okay.
One thing is you have this like notation. It's a little surprising to me. So like on the 3,133, there's like an extra leg that's going to the top.
Yeah, it doesn't. I mean, it doesn't have.
Couldn't there
to
also
go
be
to
a left
here.
such leg, or the notation just isn't what I'm guessing? Yeah.
So this, yeah. So this we should have one leg, like, but it can it doesn't have to connect here. It can connect to here too.
Yes, but also couldn't there be kind of, I don't know what the notation is, but couldn't there be like lots of legs, not just sort of like.
Yeah. I mean, so here I have 3, 3, 3, right? So
Yes.
1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1 is this one.
but you could have like 3,1 and 3,1 in another leg or something. Because the notation you wrote is just A, B, C, D.
Yeah, this is exactly A, B, C, D. That's it. No, in the rank 2 case, yes, this is what it is.
Mm-hmm. And also, can you explain a little bit how the numbers like 4, 2, 2, 4 are reflected in the module?
Yeah, so for instance, this is 4, 2, 2. This is the core, A, B, C, right? It's actually quite easy. A is the number here attached to this white vertex, 4, right? Mm-hmm. And then I have 2 and then 2.
But in the module.
Yeah. In the module.
Yes.
Yeah, that's our procedure, which is not trivial.
You can't just say it. Yeah. Okay.
I think I can, but I should tell it to you separately, maybe, because it is cumbersome, a little bit cumbersome.
Sounds good. Thank you.
Yeah.
Okay. Any other questions? No. So it doesn't seem to be the case. So thank you very much, Emine, again.
Thank
and
you.
Maybe we should thank also all the speakers of the afternoon. So thank you, everyone. And yeah, I guess I should say see you tomorrow, or yeah, I don't know, but okay. So see you then.
She's not.
Yeah, this one's from Argentina. Long time ago.
From online. I'm not happy to sit.
No, I find it impossible.
I don't want to be seen leaving the building. Come on, exactly what Sure. That's right. I did check. Yeah, that's the one.
Last time I wrote this in addition to yeah. I mean, I guess you did try. Yeah. Yeah, it's not so much. It's actually kind of as far as the.
Okay. You have a participant.
Hi.
Yes.
Yeah.
Okay.
It's very small.
Well, I had already thought that. Probably I just thought that's already.
Yeah, it is a bit unfortunate that it's in parallel. Yeah.
It's not unfortunate. We get that lucky.
That's
Well, yeah.
Yeah, or yeah, I'm sure I should try to start it somewhere. Ah, okay. Okay, so after. Yeah, there are. You try to have it over the years. Yeah.
Well, it's actually fair. Oh, good.
Yes, yes. But I mean,
That's
so we
right.
have, yeah.
That's right.
They say they should do it, like they don't like us to do it. And wait to see what is going to happen. So if they will do it now, we can leave it for later. Yeah. Yeah, so yeah, it was like that. Most likely, it wasn't as bad as
Yeah, it's good. I'm always pleased to see those. You actually face it. No.
You have an extra decoration. Yeah, so it's basically just this blown off. Just inside. Yeah, you just have this like in your office.
It's a finite in your
Infinite.
Infinite.
Because you have that, you have basically change obviously the big complex that.
Now we
With
just-
a point that's might a bit different possibility. But everything just a linear order, so it's really, I mean, it's literally some chill it just complicates stuff. But I mean, I don't, yeah. that's the equation. So the point, it's not one of the equation, but it's just the point of that. Then after equivalence, it's the equation. So the ones where only the equation is slightly more general. So the more general is not. So just the computer equation.
So the equation is.
Well, we still have of these, I mean, of these points of that. But after equivalence.
That's in the two different places. That's going back.
Yes.
And then you get.
As long as you restrict to them. Otherwise, you get some extra ones. Otherwise, you get, oh, you do not get that many extra ones actually. So if you get some extra ones. Yes.
You actually get a finite is that. It's a small extension. And is it sort of that? Is it direct? So that's what it feels.
So.
But I think
you are
or maybe I mentioned.
Oh, yes, what I meant, yeah, sorry, I meant the product.
Yes,
Yes, absolutely. So, yes.
Okay, got it.
So it is the product of that. I don't know if you can. Yes, yeah, so it's the product. But once you collapse, I don't know how you can make there's another way. We include this extra the elegant way to phrase this.
So you feel that's more descriptive than say.
I mean, you have to product word like once you collapse. Yeah, just three things, yes. Well, at most 3 things. Because if it's not an adjacency or a singleton, then it doesn't matter. You just get the point in the middle, right? And then if it's a singleton,
it's not
a very small linear order. Yes.
Because it varies. It's the thing where you get varies.
I like that. I'm just gonna go with that. Check.
Yeah.
Are you okay?
Yeah.
I just need to go.
So I could write that.
Okay, cool. See you. I don't like this. I don't like this. I want to move everything.
So something like that.
Yeah. And use that camera for some other board.
Oh. That could be worth mentioning to the.
I already did.
You did. What did they say?
We will be doing some modifications. Is it that or has people who's going to? Because we have just one more whiteboard tomorrow and one more day after that. Just try to make it better, or let's try to switch the speaking.
Okay.
One or two, but they,
Yeah.
of course, they are here, maybe they're teaching or whatever. But anyways, I want to move this because I don't think this is good for.
It's quite nice spacing comes to space.
But Or maybe we can pick one like this here. Some people.
Yeah, okay.
Right.
See you later.
This is where I have to plus.
Or did you want the two together to one side or in the middle or? All together, or in the middle, one side or in the middle here.
Okay. Just continue to use the mixer there, I think that's fine.
Yeah.
Yeah.
So if we put it to the side.
This side,
yeah. How many people is this in total for?
So how many are
27.
we?
Was it 27? Yeah. Because what you can do is you can space them out a little bit. Because at the moment you've got 64 chairs, 24.
Yes.
So, yeah. Okay. This way. Yeah. Okay.
Who's in the camera? There's a board.
Yeah, we have. If you want, there's one in the story, you know, the small black circle. That's what I mean. Yeah. Front. You said you wanted a smaller one for. Oh no, sorry, my colleague's very.
Oh, meeting is still running.
Yeah.
Oh, okay. Oh, there's 358. 358.
Remove green.
Well, you see, oh, yeah.
Straight line, especially if you know, I mean. Yeah, that's why I do a straight line between the two tables.
Oh, yeah, this one.
Yeah.
Just onto the text first. Yeah.
And then this one we're gonna have to regroup. And the other one.
The headache.
There's nothing.
I need a bit more length on that one.
Okay then. Oh, here it is. He's extended, right? But then he's just. The focus. Look in the video settings. I think it's. Do advanced.
Yeah, I think that's, this is fine. The important part is that we have to make the speaker not to stay from the camera. So if they move, if you move to the other board, then that's fine. But now the viewers online have to switch screen to go from one board to another.
That just gives a bit more, just I'm more comfortable with that with people. Yeah. Okay, I'm gonna go. Yeah, no, it's fine. You could go if you wanted to. You could control your gap by coming this way a little bit more. I know you probably don't know that.
They push something behind, you know, and even if they don't have a microphone, some people like to like chat among them.
Okay.
And they prefer not to have a microphone next to them, you know, like 2 or 3.
Did you want?
So we tell so for example, if we take the Russians to sit there when they are chatting alone. I think
Just thing here? Yeah, just don't want it to get hit. So no, I'm going to take it? Yeah, okay. Okay. So these connected, better this coming to it. Because I am just with this one. Run the down, you're going to go through. Right, Pete, the wish list, if you had a Bluetooth system, would it work?
Huh?
If you had a Bluetooth system. You know that one?
Yeah, that one had up to 4. So it works.
Is that the one that we were thinking of?
The Sunrise team connect. Yeah, they don't do it anymore, unfortunately.
Which makes you think that it was good because they don't need it for short period of time.
They did one, then they did a Mark II, Yeah. I don't know.
All okay, yeah, no, we were just, we're a bit, we tried to perfect some finesse and thinking about how we can improve to make your customer journey better, so we're just working on it now, so. No, absolute pleasure, see you tomorrow, yeah? Okay, thanks.
Force, the back row.
Maybe want to go for this, you could have done a T shape. Just thinking, could you lost your back row and have a T? And then have two people that would test it to T. So you could work out what the front of it, so you have that.
If we had that team connect and then have a third 6 foot and put the mic there, you mean?
Yeah.
Could work, yeah. We'd have to get creative with our blocks, but yeah.
And that's the sort of thing, you know, we've all done it, aren't we? But you know, we need to try to think about things differently. Yeah. So it's almost challenging yourselves, pushing yourselves away from what you've done. Yeah. You okay for one of us?
Yeah, this one we can.
That would be 3 recommended. Thank you.
Please. So, yeah, no corner. I'm just going to end it. Then, so you've got it set up so it sends to the cloud. On the computer.